the inverse sine function, \sin minus $1. Hello everyone. Let's begin our lesson on the inverse sine function. To start, let's recall a fundamental concept from our previous sections. For any function to have an inverse, it must be bijective. In simpler terms, this means the function must be both one-to-one and onto, ensuring that every input has a unique output and vice versa. However, when we look at our standard trigonometric functions, we run into a problem. These functions are periodic, which means they repeat their values at regular intervals. If you think about the graph of a sine wave, it goes up and down repeatedly, hitting the same values over and over again. This periodicity creates a challenge. Since the function is not one-to-one, meaning multiple different inputs can produce the same output, we cannot simply define an inverse for the function across its entire domain. Over the next few slides, we will discuss how we can overcome this obstacle by restricting the domain to a specific interval. The need for domain restriction. Now, let's delve deeper into why we encountered a problem in the previous slide. The sine function, which we denote as f of x equals sine x, is what we call a many-to-one function. To illustrate this, consider that the sine of 0, the sine of pi, and the sine of 2 pi all result in the same output value, which is 0. Because multiple different input angles produce the exact same output value, the function is not one-to-one. Consequently, the sine function does not have an inverse if we attempt to define it over its entire natural domain, which is the set of all real numbers. To overcome this limitation, we must restrict the domain of the sine function to a specific interval. We are looking for a section where the function is strictly increasing and takes every value from -1 to +1 exactly once. This will allow us to create the bijective condition we discussed earlier, which we will define in the next slide. Restricting the domain. Now that we understand why the sine function cannot have an inverse over its entire domain, let's look at how we solve this. To fix the issue, we choose a specific restricted interval for the sine function, which is from -π/2 to π/2. Now, let's examine the properties of the function within this restricted domain. First, the function becomes one-to-one, also known as injective. This means that within this specific window, every unique angle we plug in will give us a unique output value, effectively eliminating the many-to-one problem we discussed in the previous slide. Secondly, it is important to note that the range remains unchanged. The function still produces all possible values from -1 to +1. Because the function is now both one-to-one and onto, meaning it is bijective over this specific interval, we have finally satisfied the mathematical requirements to define an inverse function. This sets the stage for our next slide, where we will formally define the inverse sine function. Definition of the inverse sine function. Now that we have established why we must restrict the domain to make the function bijective, let us move on to the formal definition of the inverse sine function. If we restrict the domain of the function f of x equals sine x to the interval from -π/2 to π/2, then for every value x in the interval from -1 to 1, there exists a unique angle theta within that same interval of -π/2 to π/2, such that the sine of theta equals x. This unique angle theta is precisely what we call the inverse sine of x. In terms of notation, you will see this written in two ways, either as theta equals sine inverse of x, or as theta equals arcsine of x. Both terms refer to the same concept: finding the unique angle that produces a specific sine value within our restricted range. Domain and range, principal value branch. Now that we have defined the inverse sine function, it is critical that we clearly specify the set of possible inputs and outputs to ensure the function remains well-defined. Let us first discuss the domain. As we have learned, the domain of an inverse function is the range of the original function. Since the range of the restricted sine function is between -1 and 1, the domain of the inverse sine of x is the closed interval from -1 to 1. To put this simply, you cannot calculate the inverse sine of any number that is greater than 1 or less than -1, as these values fall outside the possible outputs of a sine function. Next, we move to the range. Following the same logic, the range of the inverse sine function is the restricted domain of the sine function that we established in the previous slides. Therefore, the range is the closed interval from -π/2 to π/2. It is important to note that the values of the inverse trigonometric functions that lie within these specific ranges are called principal values. Specifically, this interval from -π/2 to π/2 is known as the principal value branch of the inverse sine function. Keeping this range in mind is essential, as it ensures we get a unique answer, which we will apply in the illustrative example in the next slide. Illustrative example. Now that we have established the theoretical foundation of the principal value branch, let us apply these concepts to a practical, step-by-step calculation to see how it works in practice. For this illustrative example, we are tasked with finding the principal value of the inverse sine of 1/2. In step 1, we begin by assigning a variable to the value we are trying to find. Let us let y equal the inverse sine of 1/2. Step 2 involves rewriting this expression in terms of the standard sine function to make it easier to solve. This transforms our equation into the sine of y equals 1/2. In step 3, we need to identify which angle produces a sine value of 1/2. Recalling our standard trigonometric values, we know that the sine of π/6 equals 1/2. Step 4 is the most critical part of the process. We must verify if this angle actually falls within the principal value branch. As we discussed in the previous slide, the range for the inverse sine function is restricted to the interval between -π/2 and π/2. Since π/6 lies between -π/2 and π/2, we can confirm that this value is valid. Finally, in step 5, we can confidently state our final result. The inverse sine of 1/2 is equal to π/6. Real-world analogy. Now, to help you visualize why we need these mathematical restrictions, let's look at a real-world analogy. Imagine a pendulum swinging back and forth. The horizontal displacement of the pendulum, essentially how far it moves to the left or right of its center point, can be modeled using a sine function. In a practical scenario, if you already know the displacement value, but you want to determine the exact angle the pendulum has reached relative to the center, you are essentially performing an inverse sine operation. However, as we discussed in the previous slides regarding periodicity, the pendulum swings back and forth repeatedly. This means it will hit the same displacement value multiple times during its motion. To avoid confusion and to get a single, unique answer for the angle, you must restrict your observation to one specific swing. This is the physical equivalent of restricting our domain to the principal value branch to ensure our mathematical result is unique. Key takeaways. Now, let us summarize the key takeaways from this lesson to ensure you have a solid grasp of the concept before we move on. First, as we established in the beginning, we restrict the domain of the sine function to the interval from -π/2 to π/2. This restriction is necessary to make the function bijective, which is the only way we can mathematically define its inverse. Next, regarding notation, you will see the inverse sine function written in two ways. As inverse sine of x, or as arcsine of x, it is important to recognize that these two terms mean exactly the same thing. Now, let's review the boundaries. The domain of the inverse sine function is the interval from -1 to 1. This means that the input value you provide must fall within this range, as the sine of an angle can never be greater than 1 or less than -1. The range, which we refer to as the principal value branch, is the interval from -π/2 to π/2. This is the specific window where our unique answer must reside. Finally, always remember that the output of the inverse sine of x is always an angle. While the original sine function takes an angle and gives you a numerical value, the inverse sine does the opposite. It takes a numerical value and returns the corresponding angle. Keep this distinction clearly in mind, as it will be crucial for avoiding the common mistakes we will discuss in the final slide. Common mistakes. Now that we have covered the definition, the principal value branch, and a practical example, let us conclude this lesson by discussing some common mistakes to ensure you avoid these pitfalls in your exams. First, let us address a very common point of confusion regarding notation. Many students mistakenly assume that sine inverse of x is the same as the quantity sine of x raised to the power of -1. It is crucial to understand that these two expressions mean entirely different things. Sine inverse of x refers to the inverse function we have been studying, which outputs the angle. In contrast, the quantity sine of x to the power of -1 refers to the reciprocal of the sine function, which is known as the cosecant of x. Please be very careful with this distinction. The second common error is ignoring the range when calculating the inverse. As we discussed in the earlier slides, the sine function is periodic, meaning multiple angles can produce the same output. A frequent mistake is providing any angle that satisfies the equation sine of theta equals x. For example, if you are asked to find the sine inverse of 1/2, you might be tempted to provide 5 pi over 6 as the answer. While it is mathematically true that the sine of 5 pi over 6 equals 1/2, this is not the correct answer for the inverse sine function. This is because 5 pi over 6 does not fall within the principal value branch, which we established is the interval from -pi/2 to pi/2. As a final reminder, always verify that your final result lies within this restricted range to ensure you are providing the unique principal value.